All right, hi everyone. You're all welcome to this tutorial, and this tutorial is quite very important to your participation in the BraTs challenge because the next phase of the challenge will require every team that has submitted a short paper to be able to submit their containerized model for the test evaluation. The test evaluation is what the challenge use to rank the performance of each model that has been submitted to this challenge. Today, we have the privilege to have Juan Pablo to join us today. Juan Pablo was part of Spark Academy in its first edition, and he served as a team coordinator, I think, for Team Kano, if I'm not mistaken. And
Correct.
yeah, while Juan Pablo is a PhD candidate at the University of Washington, and his research is around medical imaging. And we're glad to have him today. I'll give him the privilege to further introduce himself because his portfolio I've known has changed a lot in the last 1 year. So the floor is yours, Juan Pablo. Would like to know more, and you can take it from there.
Great. Thanks, Raymond. So,
Yeah.
so today I'll be giving my talk on BraTs model containerization and test evaluation. This is a topic that's like really important to me, and I think we had some issues last year in the Spark Academy where a lot of teams were developed their solution and their model all the way throughout the summer, and then sadly they weren't able to submit because this containerization step was kind of confusing. So I'm hoping with this tutorial we can raise the amount of people that can submit, and hopefully everybody this year can submit their algorithms to BraTs. So yeah, with that in mind, let's get started. So today in today's talk, I'll be splitting it up into 5 sections. First, I'll give some background about the challenge, and then just introduce some terminology that will be relevant to us. I'll then go into Docker, just dive into Docker, how to create a BraTs container, specifically a Docker container. Then I will show you guys how to test and submit these with a live demo, um, and with material that you guys can be able to use yourself when you are submitting, I think will be really helpful. And finally, we'll conclude and we can have a full discussion with any questions that you guys have. Um, with that in mind, feel free to interrupt me at any time. You just unmute yourself and ask me any questions if something is confusing. Um, yeah, thanks. Let's get started. So we'll start with some background. First, just to get these out of the way, I know this might be repetitive to all of you, but I think it'll lead nicely into the next point. So the Lighthouse Challenge contains 11 unique tasks addressing key issues in brain tumor segmentation. So each task contains MRI scans of brain tumor patients, and with the disease regions are labeled by multiple radiologists. In task 5, which is what I think a lot of you guys will be participating in, this is developing state-of-the-art glioma segmentation algorithms for underserved sub-Saharan African populations. This challenge was organized by some of the co-organizers of Spark itself. So Maruf is on this paper. I know Raymond is on this paper as well. So this is great that we can work with also the authors of this paper. It's really exciting um, because they were able to provide this great data set, which sort of encompasses this distribution or this kind of population that we're not very used to seeing in these big data sets. So as part of the challenge, participants, you guys will submit four 3D MRI algorithms which take four 3D MRI contrasts as inputs and produce 3D segmentation masks as output. And importantly, and kind of the point of this talk is that these submissions should be made as Docker containers. So to get started, we're going to review some terminology. You guys are familiar with the four MRI contrasts. These are what goes into your algorithm. These are post-contrast T1 weighted or T1C, T2 weighted, T2W, and T2 Flare, as well as native T1. So as we move forward, these will be referred to as inputs or input volumes or for contrasts or input scans. So this is kind of the terminology that you'll see people use in different talks and presentations. Um, so I just wanted to make sure this was clear as we move forward. Yeah. Um, then as we step forward in your pipeline, we reach the first step, which is something that you guys worked on, is pre-processing. You guys pre-process the images to make them sort of be in the right format that your algorithm will accept. So you do this pre-processing step, which is then followed by the trained model, which has been evaluated and improved upon by optimizing a loss. Finally, you post-process your model outputs. And then these model outputs are what you submit as to the BraTs challenge. But just to get more familiar with the terminology, this entire process, this entire sort of algorithm that you're building, or this, it's called a framework or a pipeline. This is what people refer to it when you read papers. So, and additionally, just this gray part is sometimes referred to as a model or the algorithm, the segmentation model, or a lot of times the unit. So once we have our full framework, we get our produced segmentation masks, and these we can refer to them as segmentations, masks, outputs, and prediction. So now that we have all this terminology, we can move forward, knowing that we have sort of the same language in mind when we're talking here. So the next step here is to use a thought experiment, which I want to kind of interact with the crowd a little bit here. Um, so for this thought experiment, our goal is to turn our segmentation framework into an app for radiologists. Here I named the app Seg Health for now, but we can work on that title. It's not too interesting. So a thought experiment. What should be true about this app? I'll start with a few things. So in this app, the user will provide input volumes and receive output segmentations. The user shouldn't worry about how to download packages, like the user shouldn't have to pip install anything. The user shouldn't have to conda install anything. Um, the user shouldn't have to worry about matching which computer version we use to write our code, um, etc. Think about when you use an app like Facebook. Are you worried about downloading conda install matplotlib? No. So this is kind of the interface that we would like to have with our app. Finally, our app should include all of the necessary components for our algorithm to work. Um, so with this in mind, I'll ask you guys a question. So which parts of our framework that I described before should we include in our app, and which parts should we leave to the user? Um, yeah, so I'll open up for a little bit if you guys have any ideas about how to answer this question. So yeah, so which parts should we include in our app, and which parts should we leave to the user to do? Um, okay, so in the chat, somebody said input and output. Great. Yeah. Okay. We can continue. So um, maybe a potential idea for what to include is just our model. Maybe our app should just include the model. But the issue with this is that the app now leaves pre-processing and post-processing to the user. So this isn't really a good place for where we should wrap our app. So the next The actual place where our app should go is around pretty much the entire process. The user should only have to work on inputs and get outputs. I think somebody said this in the chat. Yep, exactly. The pre-processing, train model, and post-processing should be our framework. Exactly. So some conclusions from this small experiment, thought experiment is that if we want to turn our framework into an app for radiologists, our app should have a simple interface which only prompts for inputs and returns outputs. Our app should run anywhere on any operating system without any setup issues. Our, our app needs to include all necessary packages and software that needs to work. It should sort of install everything itself so the user doesn't have to do any installing manually besides just installing the app. So the solution that we can come up with and the solution that's commonly used is to package all of these app commands and a version of our entire environment, such as code, libraries, and even the sort of operating system into a shareable format. So we can collect everything that we use to generate our app. We can freeze it at a moment in time and then turn this into something that we can share. And then when we share it with somebody, they can sort of use this version of all of our code libraries and operating system to run the app themselves. So this shareable format is called a container. With this in mind, we'll dive into Docker containerization. I'll give an intro into Docker and containers. I'll talk about how Docker works and how to create and run a container. So following from before, containers are used to package up our code and all its dependencies so that application that we develop runs quickly and reliably from one computing environment to another. Um, Docker containers are the industry standard for working with containers. You'll see them used by every big company, Google, OpenAI, Netflix, Spotify, and you'll also see it a lot in research and in academia, where you'll see people where a key goal is reproducibility. If you have a new algorithm and you want somebody to test it, you want to make sure that they are doing a good job testing it. They don't make your algorithm look worse than what it is to make themselves look better, or the other way around. So it's really advantageous to use Docker containers to make sure that everybody's code is working as it should. Um, so before we get started with submission, um, maybe not right now because in the interest of time, but you'll go to docker.com slash get started and you'll download Docker Desktop, which will give you a nice interface to work with Docker environments, Docker containers. And for a deep dive in tutorials, here I'm going to be giving like the um, sort of a superficial view to get you started with the BraTs challenge. But if you want a really deep dive, I recommend the tutorials in docs.docker.com. They're really comprehensive and they have a lot of videos, so these should be really helpful. So with that in mind, let's get started. This is how we'll create and run a container. So there's some key terminology that we'll be using to run a container. A Docker container requires three stages. First, we'll create a Docker file, which will give us the instructions that we'll be using to generate our compiled Docker image. So using the Docker file, we'll do this operation called build, which will follow these instructions and generate what's called a Docker image, which is sort of this file that contains all of the dependencies and everything already installed. Um, you can think of it as a compiled version of our code. Um, and then finally, once we have this compiled version of our code or our app, we can essentially run it. And by running the image, we're doing what's called Docker container. So I'll go into more detail now. So it seems like the in all of these tasks, kind of the main idea is to create this Docker image, and then after we have this Docker image, we can use it to run a Docker container. So this Docker image is really an important part of this process. They're the foundation for running a Docker container. Um, so the image is a package snapshot that includes all the files, binaries, libraries, and configurations to run an app. Images are built using Docker files, which I'll go more into detail in the next slides. And each Docker file instruction, like copy, run, and CMD, adds what's called a new image layer. So image layers, images are built kind of in this sequential structure. So we can start kind of from the bottom up. So first, what we start with is um, sort of the operating system and the platform. So all Docker images are built on Linux. In this case, we're using Linux and AMD 64. So our code will work with AMD 64 CPUs. And this is the instructions that were given to us by the BraTs organizers because this is what their CPUs will look like. Then once we have our operating system and some Python packages, because we suspect that we'll be using Python, um, we can run some system setup commands like apt get update. This one, apt is what you use in Linux to get commands, maybe similar to pip, but so you need to update this app manager when you're creating your new image. Then we'll copy our requirements.txt, which I hope maybe you're familiar with, but this is a text file that will include all of the Python packages that are relevant for our pipeline. So we'll copy this from our local um, sort of directory into the image directory. So copy requirements.txt to dot here. Then we can run pip install to install this in our image. It'll install all of the packages. And then we can copy our actual code and our repo and all of our logic here into the directory as well. So all of these are kind of setup steps, which you'll do once when you are compiling your image. You build your image and it'll run all of these steps. And then what you'll be left with is this code, which contains all of the packages already in this um, tight format, basically. So then when go to use your code, what they'll do is they'll download this, and when they run it, the Docker container itself will be equipped with this CMD, which will do which will be the final command that will run when your container runs. So in this case, the command is python main.py. So once this is built and this image is built, we can run it as a container. Um, Now I'll be going into more detail about the Docker files. But before this, I wonder if there's any questions. I'll give about like a minute in case somebody has questions. Feel free to reach out. Feel free to unmute.
I think we have a question in the chat.
Okay.
It says, do you store the checkpoints also in the containers?
Yeah. Yes. Yes. So I'll go into more explicit detail about what is included in the container moving forward. Um, but yes, so the checkpoints are important to run your models, and they'll be copied here in this step when you copy your app code. So here I copied only the main.py, but in this step you'll actually be copying your entire code base and everything that you want to be included in the container. Yeah, great question. Oh, yeah. Thank you, Aniakan, for the comment saying that you can get your requirements using pip freeze and then side caret and then requirements.txt on your shell. So this will sort of freeze your whole environment and then put it into the requirements.txt so that you can easily run pip install with it. Um, okay. So with this in mind, I'm going to move forward. So now that are familiar with Docker images and what they contain, I'll go into more details on the step on how they're generated. So these images are generated with what is called a Docker file. So Docker file contains all of the instructions that we use for building this Docker image. It will tell Docker what you want to place in the container, which packages you want to have in the container, and what you want to run. And similarly to as I described before, we follow this sequential structure to build the image from the bottom up. So we start with the sort of Linux architecture and we go all the way to the command. So let's zoom into the Docker file. This is actually the one that they recommend on the Synapse tutorial website. So this is might be even the one that you end up using for your submissions. So the first line is the operating system or the CPU architecture. So we talked about this before, but we see that you can also even bring in another image and start from there. So in this case, we're starting with a PyTorch image, which with some CUDA support enabled. So the specific CUDA 12.1, cuDNN 8 runtime. These are the specific drivers that the CUDA GPUs CUDA-based GPUs will use for running the code. So these will actually be compatible with the challenge organizers GPUs. So this line here, it's recommended that you don't change this moving forward, and that will be included in the supplementary materials. So you can look there. Um, then this line runs apt get update. We update the package manager. Um, Here we're installing all of our Python dependencies using pip install. So as we said before, you copy in requirements.txt and you copy it to local. Then you run pip install pip to have pip installed. And then you pip install all of your requirements, which somebody mentioned in the chat that you can get with using pip freeze. And I think there's a similar command for Conda to get all the packages into this text file. So I will say that sometimes not all packages make it when you do the pip freeze. So as a sort of a workaround, I recommend that you use this as the first step and then you sort of refine and test it to make sure that all the packages are included in your requirements.txt. And then answering the question in the chat. In this step here, we copy the rest of our contents of our repo. So here we can copy our tools directory to a internal tools directory within the image. We can copy our checkpoints in, and then we can even copy our main.py in as well. And then finally, this is the command that will be used by all of your BraTs images. You'll do Python main.py -i input -o output. So dash I will point to the input directory where the files will be, and dash O will point to where the files will be saved or the output files. Um, okay. So now we'll go into actually building this image. What are the commands that we use to build it? So once we have configured our Docker file and have all our app code running and everything, we're ready to build our image. So to build this, we can use this command. It's very simple. It's Docker build dash T for tag. And then we'll give our image a name separated by colon and then a tag. So the image name can be anything you'd like, but it should be something that is informative so that we can reference to it later. And then the tag can be sort of like a version number. So you can use like something like V0 or V1 or latest. And then there'll be a space here, and then you'll point to where your Docker file is. So what this command will do is it'll actually point you to it'll go to the Docker file there and look for this Docker file. and then build and sort of tag it with this name. So after building, you'll have these commands like this, which will basically show that your Docker file is building and that everything worked fine. Or you'll run into an error, at which point you'll have to figure out some way to fix it. Now, for running this container, now that we have our built image, we can actually run the container or the app. So an important point here is that once we have compiled our image into this into an image and it's like this binary code with all the packages installed, we can use this image to start as many containers as we'd like. So you can think of it as after your app is built, infinite copies can be downloaded off the App Store or any Play Store. Um, but the app is already built and it's already sort of in a fixed location in a fixed state. So anybody can download it as many times as we'd like. Um, so to run this container or to like open this app, what we use is the terminology Docker run, and then the tag name that we assigned it before. Yeah, so I went into a few details on how to actually use Docker. Now I want to give a little bit of insight, kind of under the hood. How does Docker work? So let's imagine the case that we have a Windows user who is trying to share their code with a Mac user. Uh, so what they'll do is they'll build an image using Docker, and the image will be written in Linux. So Docker installs this Linux virtual machine, sort of this very small Linux machine, which allows you to compile your code into a Linux language. So once your compiled image is made, it'll be in Linux, which is kind of this universal in-between language. And then a Mac user will also have installed Docker, so they'll also have this sort of Linux virtual machine, this lightweight Linux virtual machine, and they'll be able to run this image without any dependency issues or any OS issues because they have this sort of like Linux and Docker interface. Um, of course, this isn't only one directional. Once we can make it to this like sort of middle ground with Linux, we can go the other way around. We can go from Mac to Windows, and the translation from Linux to either of these is also here because obviously we can go from here to here and from here to here, from middle to right or middle to left as well. Um, yeah, okay. So before we get started, moving to actually creating the BraTs container, now that you guys are familiar with how Docker works, do we have any more questions? Let's take a quick break here.
I think we have two in the chat.
What was the model? Um, so, sorry, Raymond, do you understand the what if the model was trained using Kaggle notebook? Oh, what if? Okay, sorry. What if
Yeah,
the model
so
was trained using Kaggle
yeah,
notebooks?
the question was asking if what of a situation where the model was trained in Kaggle. I think it doesn't make a difference as long as you've saved your checkpoint and um, you can build the Docker containers as well. But that was what the question meant. Some teams train their models on Kaggle.
I see.
Yeah.
So I think for this, the main, I think yeah, like Raven said, there should be no issue. But we just need to translate the code from the inference code from Kaggle to a .py file. Um, yes. So turn your code into an inference function, and then that should work. Um, And then was there any updates related to Docker submission earlier? Yeah.
I'm not pretty sure of that question.
Yeah,
Maybe the person can unmute. Or Imana, you can. Okay, no, that was trial hard. If you can unmute and ask your question. Are you able to do so, trial hard? All right.
okay. Sure. Yeah, no problem. Yeah, we can keep going.
Yeah.
Now we've just kind of reached this point where we are familiar with Docker containers and some general terminology. So, um, translating this into a BraTs container requires that we go over some ground rules set by the challenge organizers to make sure that we don't run into errors when we submit our containers. So, first and foremost, um, there's this concept of Linux file permissions, which determine who can access files and directories on a system and how. So there's read permissions, which allow users to view the contents of a file or list contents of a directory. And importantly, you cannot write to files in this directory if you have read-only permissions. And then also there's write permissions, which allow users to modify the contents of a file. So this includes writing, adding, or changing or deleting content. Um, and if it's write only, if you can write in a directory, then you can delete, rename, or create new files in this directory. So, more concretely, when you work with your container, you're going to be working basically in these four um, different kinds of directories. So, in the input, which is where your data will be stored, you will only have read permissions. You won't be able to sort of save intermediate calculations. You can't save them here because all you can do in this directory is read the files and load them. The output directory, which is where you'll provide your output segmentations. These have both read and write permissions. So you can read here any files, and you can write as well. This TMP / temp is a temporary directory. In this one, inside your container, you'll have full access. You can read and write in here. So this is sort of where we recommend that you do all of your intermediate calculations, and this is where you should sort of store any, if your model produces something and then you do post-processing after, this is where you should store the model outputs before you do post-processing if you're doing it in two steps. Um, and then anywhere else, once you are inside the Docker container, you will not have any read permissions or write permissions, and you'll have an error. Um, so yeah, just wanted to make sure this was clear. I think there was a lot of issues last year, and this is kind of generally how the BraTs organizers expect your Docker container to be organized. Um, and then so your input data will be mounted to this /input directory inside the container. And as I said before, this will have read-only permissions. And you can expect the input data to be structured like this, similar to the training data. In the case that you're participating in SSA or Sub-Saharan Africa challenge, this will be BraTs SSA instead of GLE, as I'm assuming you guys are familiar with at this point. And you'll have the four input contrasts. Um, and the predictions are expected to be written to /output inside the container, which has read-write permissions. And as you can see, for each subject, you will have one Nifty here. So make sure that your files have this naming structure as well. So you can even use the directory name to help you name the save file. So I'll go into a little bit of how they expect your file structure to be in the Synapse tutorial. They show that your repo can have checkpoints where you'll place your final epoch or your epoch that you'd like to use for inference, your Docker file, your main.py where you'll actually run your code, your requirements.txt, which we mentioned before, and then all of your tools such as inference, post-processing, pre-processing, read-write, SITK, and torch packages, etc., and all of your functions. Um, and then your Docker file will be basically the one that they recommended is exactly what I had mentioned before. And you want to make sure that your code that will be in the main.py, you're going to make sure that you can run it with Python main.py dash I input path dash O output path. Um, okay, so with this in mind, I'm going to switch over to the sort of the second part of this talk where um, I work with another Spark sort of team coordinator, Tawfiq. If you guys are familiar with Tawfiq, we worked on creating this starter template where it'll help you get started with submitting to the BraTs challenge and making your container. So I'll share this link in the chat. Um, okay, so I'll go to this link now. And this template is something to help you get started with submitting. Um, so what you'll see here is in the README, you can sort of go through this, and here is the sort of official submission guide by Synapse. You can click on this, and it'll lead you to these instructions that were contained for a submission tutorial for Docker. So this is sort of everything that I've outlined in this talk so far in one pretty clean document. It's really helpful. And then here, oh yeah, um, so I think somebody raised their hand. Oh, okay, okay, sorry. Can you guys see my screen still?
Yeah, we can see your screen for sure, but
Uh, can you can you see the GitHub?
no,
Oh,
we are not seeing
okay.
the GitHub. Now we can.
Okay, great. Sorry about that. So yeah, once you go to this link, you'll be led to this GitHub template, which will contain basically the full skeleton for your submission for BraTs if you'd like to use it. Um, in the README here, I point you to the official submission guide that will lead you to this BraTs submission tutorial, which will contain all of the instructions for submitting your Docker container. So to quick start with this repo, we'll do git clone in our terminal. So if I open the terminal here, oh, we can get started by um, um, I'll make a directory where we can just use this, and then we can git clone into this directory using this command here, git clone into this repo. And this will download all of the necessary files along with some helpful information. Um, so the repo is laid out in this structure. It contains everything that was mentioned before, such as the Docker file. It contains a bash script that'll help you build and run. It contains requirements, checkpoints, etc. And these are kind of all placeholders at this point, but they can help you get organized. Um, so yeah, so once I open this, we can see here um, that the repo sort of contains everything that you will need. Um, okay. So now we can get started with um, how to actually submit to BraTs. Uh, so yeah, so I'll get started with this part here. So that the first step to submit is to log into the Synapse Docker registry and use your personal access token when prompted for a password. So in this case, what we'll do is we'll go to Synapse um, and we'll make sure that we have our personal access token. Um, so I actually have this from a um, previous attempt, but the instructions to create this personal access token can be found here. So I'm just going to copy mine from my notes. Okay. So then what we'll do is once we're in our directory, um, so once we are in our, sorry, let me get clone again. Yeah, so once we're in our directory, we'll be able to run this command that says docker login docker.synapse.org -u and our username. So ls, and so I'm here inside the directory, and what we can do is we can run docker login this command here, and my actual username is Juan Pablo. And then for the password, make sure that you use your personal access token, which can be again found using this link. And this will basically make sure that you can log in successfully. Um, then I'll open up my editor. Can you guys still see my screen? See VS Code?
Yeah, we can see the VS Code.
Okay. Um, okay, so let's have this here. So now what we can do is we can fill in this bash script. So this bash script contains all the instructions for building, running, and submitting a Docker image. So we'll fill this in with our project ID here, our image name, our tag, which I just leave as latest usually, and then Docker file dir. Since we're inside the directory, this is a current working directory. And then we can do the input dir. As an example here, I have provided some example input data in the GitHub repo, so you can even just leave this as is when you're testing. And then you will change your username for your actual username. So I'll go ahead and fill this in now. Um, the project ID, there's instructions here on how to get a project ID if you don't have one yet, but I think a lot of you should already have it since you submitted to the validation stage. Um, um, okay, so I'm gonna go to my project here. This is BraTs 25 Kurt Lab, which is just kind of our project that we're using for Kurt Lab. And I'll go here to where it says project SynID to actually copy it to clipboard. Can you guys see my screen still, my Synapse?
Yeah.
Okay, okay. So I'll copy this and then I'll just fill in the template here with my actual project ID. Um, I'm gonna log in again here on VS Code. Um, So to do this, what I'll do is I'll um, CD into here, and then okay, I'll CD into the template, and then what I can do is I'll uncomment this specific step. So this step here, I'll just uncomment this line, and then I'll just do bash build and run commands. Um, so this will prompt me to log in since it's going to run this line. And once I provided my password, I was able to log in again. The next step is to Docker build. So I'll use this uncomment this next line here, which will fill in the project ID, the image name, tag, and Docker file dir. This is exactly how the BraTs organizers expect you to organize to name your images. So what this will do is it'll go through and actually build using the Docker file, which is set up to run Python main -i input -o output. And the template that I shared already has sort of some um, very minimal logic to do the input argument loading and output argument loading. So it'll basically run this main with your input dir and output dir here. But reminder that this is empty. This is kind of a placeholder. So make sure that you fill this in. Um, so once I have uncommented this, I can run Docker build, and this will run the build commands as I said previously. So it'll build, and once you see successful, when it successfully built the image, you'll see this command here, building um, the time and then built finished. So if not, you'll have some errors. Yeah. Does somebody want to have a question? Sorry. Oh, okay. And then, so once our image is built, we can see it with Docker images ls. Sorry, Docker Docker image ls. Sorry. And sometimes it doesn't load for a little bit. Um, oh, maybe, okay, I'll make a new one because I think I've made this image name before. So let's just start from scratch. So BraTs SSAA Spark demo. So this image will be called this. And then I'll just build it again using um, the same command. And then, yeah, so here we can see that the image was generated. BraTs SSAA Spark demo, the latest. I think last time I edited the code was 10 hours ago. So you see here that um, actually this is a pretty big file. And the first time that I created this image, it took a longer time since it had to actually download all of this. But Docker has a feature where if you make changes towards the end of your Docker file, so if you change, so we remember how it's sequentially built in this kind of bottom-up approach. If you change the things sort of on this end, the Docker file will be faster to rebuild. So if you're making a slight modification on the bottom, the Docker file will make sure that it doesn't re-download all of these sort of previously done operations, which is a really useful feature. Um, so then once we're ready to run the image, we can go to step three. This step three is where we can run the image with when we have no GPU and we'll have no network access. So this is sort of simulating what we'll be using when we're submitting our BRATS challenge, but without GPUs. So this, I know I don't have a GPU on my local computer, so this is helpful for testing to make sure our algorithm is working well. So I'll uncomment this line and then we can just run it again. And what we see here is that this warning where the requested images platform does not match the detected host platform, and no specific platform request was made. Um, so this is kind of a warning, but it's not really an error. This is because my current platform, my current computer doesn't have um, this like Linux AMD 64, but this is what the challenge organizers will have, so it's good that we keep it. So this warning we can kind of ignore for now. And then these are just, we see that the model was able to, I mean, the container was able to run the main.py where it printed like input directory and it told us that, and it printed, it was able to print like running inference using these file paths. Finally, it also was able to make it to the point where it saved the prediction to save path. So right now it's not saving anything, but this is just kind of the kind of outputs that you can expect to have when you run your container to make sure that everything is running smoothly. Okay. So just a little bit more about this command. The Docker run, it'll show that it has network none. Here in this point, we have zero NVIDIA G visible devices, so zero GPUs. Our input directory will be fed in from this variable here. But this is actually just a good template to use because this is the exact template that they'll be using for the evaluation. What they'll do is they'll just change this variable here. Um, and then docker.synapse.org / project ID. This is kind of the name of the image that we had before. If you have a GPU, you can use a step 3b, but it's optional for now. This will be the actual command that they use in Synapse. This is the command that they provided as well. And you can see that it has this GPU's all step, which won't really work on my computer. So yeah, if you have GPUs available, feel free to run this, and this will give you the most accurate test for your um, to see if your code is working. But if not, you can use this step 3 no GPU version. And then finally, once your container has been successfully run and you have your image and once you have your image and you run your container and everything looks fine and you see that in your output directory, you actually see segmentations, you can push your image to Synapse. And this takes a long time because of, as I said before, this file can be like pretty big. In my case, it's 12 gigabytes, but I think for a lot of your guys' models, it'll be maybe even bigger because I actually don't even have a model here. So what you'll do is once it's ready, you can use this command, docker push docker synapse.org. And then, so basically docker push and then your Docker image name, which is the same one that we've been using previously to run and to build. I'm not going to run this here because it takes a long time, but I ran it previously. Can you guys can still see my screen, right? I switched to PowerPoint now. Okay. So in the slides, I pretty much just went through everything that we went through. I will do Docker login using our personal access token. We'll push our image to Synapse using this and make sure that when you create your personal access token, you have permissions to do push and pull, etc. I usually just give it the personal access token full permissions to avoid any issues. Um, and then submitting to the challenge. So after you push, your image should be available in the Docker tab of your Synapse project. So I'll actually go through this now. So I'm here in my Synapse project, and what I'll do now is I'll go to this Docker tab, and you'll see this image that I uploaded yesterday. Um, so then I'll be able to click on this, um, and we can actually click on Docker repository tools and submit Docker repository to challenge. Um, and I actually don't have like any code in here, so I haven't committed. But once you actually do commit, you'll be able to submit here, and it'll ask you a few questions, etc. Um, yeah. Okay. Great. So with that said, this is all I have for today, but there's additional resources that are included in the um, GitHub that was included. So a lot of you guys will be submitting NN unit. NN unit is like a popular segmentation framework, and it provides really good out-of-the-box performance without much configuration. But packaging an unit into a Docker is quite complicated. And there's a lot of places where you can go wrong. Um, so Tawfiq has kindly prepared a very helpful Docker image and sort of all the surrounding code, such as Docker files, etc. He provided a very helpful example that you can use that'll help guide you with using the NN unit in your final submission. And this is also in the GitHub. You can find it in the um, additional template directory here. So if you go in here, you'll find like NN unit. Um, this is like the NN unit source code, and then here's like the Docker file that he used. You'll see it's very similar to before, but with some additional sort of packages installed. Um, yes, and there's additionally um, this section that they mentioned in this tutorial, um, where if you're still having issues despite being logged in and pushing to your own Synapse project, so if you followed all the instructions from before and you're still having some issues, there's this section in the tutorial where they say click to expand section, and I encourage you to look into this if you're having issues. But if not, um, no worries. What this will do is it'll point you to an alternative way to submit your Docker container. Instead of submitting it to Synapse, you submit it to Docker Hub. This is another registry where your container images can live, similar to GitHub, where you can upload your code here, you can upload your containers. Um, so what this will point you to do is you upload your container to this directory, and then you can find a way to connect your Synapse project to the Docker Hub image, basically. So do this if this like original instructions don't work. If you still can't connect your login to your terminal, for example, or if your Synapse upload isn't working, this might be a good alternative. But yeah, I think these initial instructions are the main thing to try and use this kind of as a plan B, basically. Um, and with that, I think that's all I have to say for today. Yeah, thanks for coming, everybody.
Thank you so much, Juan Pablo. Um, so I can see that the slides are available on GitHub. I don't know what GitHub Taufik is referring to, but if you don't mind, if you can send me an email of the slides too, so that we can have it shared as well. Thank you so much for this session, and thanks to Taufik for working with you on this. I don't know if anyone has any other questions.
So I think somebody raised their hand. Yeah, feel free to unmute or to, yeah.
Sure, you can go ahead, Taufik.
Yeah.
Yeah, you
Hi.
could.
Can you hear me?
We can hear
Yes.
you, Taufik.
Yeah, I just wanted to add on for some of us that might not have enough compute to run the Docker locally. You can consider working on this environment called Lightning AI. It's just like a VS Code environment, but it's in your browser. And then they also give you access to GPUs and CPUs. And you don't have to install Docker per se. The same way Juan Pablo did, you can do that on there too. Yeah.
All right. Thank you so much, Taufik, for that. So we're going to use the Spark Connect for any questions with regards to the Docker. And I'm going to add Juan Pablo to the Connect definitely, because we normally have a group where we meet and just communicate during Mikai. So I'm going to add Juan Pablo to to that group. So just in case you have any question in the process, and you need to ask someone some question, Taufik is already in the Spark Connect group, We're going to add Juan Pablo also if he doesn't mind. So you can leave your questions and comments there. And it's also fine for you to just say, oh, guys, I made this mistake. This is what I was supposed to do, and just put it in the group there. Owimana just said, if we are doing assemble, will you advise us to do one container or multiple container for every model? Juan Pablo.
Yeah. So I think Tawfiq answered that. The best way to do this, I think the simplest way is to make sure you have one container. So at the end of the day, they want to make sure that they can run your code with one single command. So they want to make sure that your code can run with just Python main.py-i this. So yeah, one container so that you can have basically one command. Um, I think this, yeah.
All right. Yeah, that would have been my answer as well, because like Juan Pablo mentioned, they don't want to deal with your models. They want to deal with the final model that you have to use for prediction. So it should be one container for your final model. All right. Any other questions? Any other questions? Okay. Before we go for administrative updates, we would like to thank Juan Pablo. Guys, please help me thank Juan Pablo for doing this. This is very key. A lot of teams have not proceeded into the next phase of the challenge because of the technical challenges around submitting their Docker. So him taking out his time to create this is quite lovely. Can we just thank Juan Pablo? Thank you so much. Thank you so much. We look forward to catching up and having fun again next month. Yeah, it's a very big one here. Thank you so much. Then in terms of administrative updates, before we close, couple things. One, Professor Idona has asked me to tell every team here that have not uploaded their code to their GitHub to do so before the end of the academy next week. So if you've submitted a short paper, most of you didn't add your GitHub URL to your short papers, which is fine because we are still dealing with the short paper. Before we head into the final submission, and we need every team to submit their code to their GitHub. We created a GitHub that we use during the foundational course. Please ensure that you push your code to the GitHub. That is one. Then two, next week is going to be marking the last tutorial session, the official last tutorial session for Spark Academy. And we'll be having Professor Charles Delahunt uh, speaking about career and what's next after Spark. Because for the last 4 months, you guys have been acquiring knowledge, starting from the basics of machine learning to deep learning. And here you're already submitting short papers considered for the BraTs challenge. So, but what's next? So we'll be having Professor Charles Delahunt next week to talk about that. And next week also, we'll be unveiling a mentorship program called the Spark Nest. That will be the first edition of that mentorship program. So it will be a weekend meeting that you don't want to miss. I would like to say that I'm proud of the progress that a lot of teams have made, to be honest. I am really proud of the quality of some of the papers that I saw and how much effort that you guys have put into this intellectual property. It's quite encouraging. And like I always say, at the beginning of Spark is always difficult, but at the end you always see things that keeps you going. It's quite encouraging that, yeah, people are actually taking this knowledge, they are putting it into work. I would like to say kudos to you all. For those that their teams weren't able to do anything, don't be discouraged, to be honest. Um, I will tell you so many instances. For instance, even Taufik that is here, I'm going to use Taufik if he doesn't mind for an example. They couldn't get to submit their paper last year, but this year Taufik is having over 4 papers submitted Tomikai alone. So it's a process, right? It's a process. So don't be discouraged by the fact that you weren't able to put out something this year. Continue and stay consistent. With this, I would like to say thank you all. Thank you so much again, Juan Pablo. And I will see you all next week. If there's any question, our WhatsApp groups are still open for communications and deliberations. Thank you so much.
Yeah, thank you so much, Raymond, and yeah, good luck, everybody.